Okay, so today we're going to be doing a problem involving static friction. That's kind of a tricky one. So if you want to pause the video, give that a quick read, we can get started. Okay, so to break the problem down for you a little bit, there is a lab, I believe it's associated with the U of Toronto, and what they do is they try and give like star ratings to winter boots. They want to see how good is a particular pair of boots at not sliding on ice. So what they do is they have an icy floor in a lab that has a couple of pistons on one end, and they can actually change the angle of the floor. And they take some poor participant, a grad student probably, and they strap him into a harness, put a pair of boots on them, and they just up the angle of the floor until they slip, until they fall down. And what that does is it gives them something called the maximum achievable angle. Okay, and the higher that angle can be before you slip, the better the boots are at preventing you from slipping. So what we're trying to do in this problem is figure out, okay, well, if the coefficient of static friction between an icy ramp and a box or a person wearing some boots is 0.2, well, what maximum achievable angle will they have? In other words, how much can you incline that ramp before this box will start to slide? Okay? It seems like we're not really given much at all, and in fact we're not, right? We don't know the mass of the box, we don't know the angle. So when you're faced with a hard problem like this, again, it's helpful to fall back on some common steps that come up in a lot of these force problems, and this is a force problem. And in any force problem, the first thing we're going to do is draw our free body diagram, okay, and sort of get organized. So what does the free body diagram for this box look like? Well, there's the center of mass of the box. So in terms of the forces that are acting on this box, we've got a normal force, which remember comes off perpendicular to the surface always, or normal to the surface. We've got gravity, which is going to be the driving force pulling it down the ramp. And then we've got a static friction, which is going to oppose the start of that box's motion and act totally up the ramp like that. Okay? So we also want to define our x and y directions, right? This is a two-dimensional problem. And it may be tempting to make up and left your x and y directions. Okay. But I mean, that'll get us to the final answer, but it'll be a pain, okay? Now, the issue with this is that a lot of our forces, right, our static friction is going to have components in the x and y direction. Our normal force is going to have components in the x and y direction. And the most annoying of all is that the acceleration of the box would have x and y components, right? And so what we can do to prevent that is rotate our coordinates so that they are parallel and perpendicular to the ramp. And that's something that you want to do pretty much anytime you have a problem that involves a ramp. Okay? So what we're going to do is, let's say the x direction can be straight down the ramp like that, and the y direction can be perpendicular to the ramp. So that's nice because now our normal force is totally in the y direction. Our static friction is totally in the x direction, but one consequence of this is that now gravity isn't purely in the y direction. It has components in the x and the y direction. So this is the x component of gravity, and this will be the y component of gravity. Okay? One other consequence of this is that the ramp angle theta actually appears right here. Okay? Now, there's lots of different ways you can convince yourself that that's true. The best way that I would do it is to, just draw the right triangle that we've just drawn right on the ramp here. Okay. Okay, so there's that triangle from our free body diagram. So we can see that if that ramp angle is theta, then by the z rule, this has to also be theta, right? If that's theta, well, anytime we have two intersecting lines, the opposite angles are the same, so that must also be theta, right? Well, this here is a right angle, So if this is theta, then this must be 90 degrees minus theta. And looky here, we've got another right angle right here. And if this is 90 minus theta, then this has to be theta. Okay, lots of ways of getting there, but you can also just remember that that's the case. But your ramp angle appears right here in your free body diagram. Okay. So now that we've got that drawn, everything's all set up, we can go ahead and do our common second step in pretty much any force problem, and that's to do the sum of our forces. So use Newton's second law in the x and the y directions separately. Okay. Doesn't matter which one I do first. Maybe we'll just do the x direction first here. Okay, well, what forces do I have acting in the x direction? Well, I have friction, and that's going to be acting negatively, right? So negative the force of static friction. And then I have this x component of the force of gravity that wants to pull the box down the ramp, and that's acting positively. So plus Fgx. Okay, and they sum to m times a in the x direction. Okay. So now we've got to think pretty carefully about what we're going to do with that equation that we've just written and think about what we're trying to solve, okay? We're looking for the maximum angle that we can have this ramp before the box will start to slide, okay? So in other words, the box will just barely not be sliding yet, which means it's going to have no acceleration yet, okay? So the other thing, right, there's a whole range of angles that won't cause that box to have any acceleration, that will cause ax to be 0. But we want specifically the biggest angle that will cause that to still be true. And that happens specifically when our friction force is maximized. And remember that our maximum friction or static friction force between two surfaces is given by the coefficient of static friction times the normal force. Okay? So I can simplify that equation that I just wrote and write it as this: negative mu s Fn plus the x component of the force of gravity I can write as mg sine theta, and those two things sum to 0. Okay? So that's nice. I mean, at least we have what we're trying to solve for in our equation right there. But there's a bit of a problem in that we have the mass in this equation that we don't know, and we also have the normal force in this equation that we don't know. So before we can solve for theta, we have to deal with that. So the sort of natural next step to do here would be to do the sum of the forces in the y direction. Okay, so that might be step 3. So what do we know about the sum of our forces in the y direction? Well, if we look at our free body diagram, acting in the y direction, we have the normal force, Fn, acting positively, and we have the y component of the force of gravity acting negatively, okay? And remember, this box at no point will ever be accelerating up or down off the surface of the ramp perpendicularly. So it's always going to have a y component of its acceleration that is 0, okay? So rearranging this little equation tells us what the normal force is. I mean, the normal force is going to be just equal to Fgy, which, again, will be mg cos theta this time, okay? So what we'll do is we'll take that little fact that we just learned and we'll plug that in up here for Fn, and that will be our step 4. Okay, so our equation reads negative mu s times mg cos, times mg cos theta, okay, plus mg sine theta equals 0. So you might see now we could divide both sides of this equation by m, and they cancel out. So that's what we were kind of waiting for. We knew that had to happen eventually, right? Okay. So we're almost done. We've got this equation down to the point where the only variable in it is theta. We know what mu s is. It's 0.2. We're given that in the problem. And we know what g is. But, oh, look at this. The g's also cancel out. That's interesting. So that means that not only does it not matter what the mass of this box is, but it doesn't even matter what planet we're on. When we perform this experiment, we're going to get the same answer. We could do this on Mars, and the maximum achievable angle will be the same. Okay. All right. So finally, doing some rearranging, we get that sine theta equals mu s cos theta. And if you know your trig identities, I know these are kind of a pain, but the only one that I would suggest that you really commit to memory, at least in a first year or a high school physics course, is this guy. This one can come up quite a bit. Very often when you're solving for angles, you're going to have to use that. Okay, so we may see here that we can write mu s as sine theta divided by cos theta, which is just the same thing as tan theta, and therefore theta is just the inverse tan, or the arctan, of the coefficient of static friction. So pretty complicated problem, but it's always satisfying when it reduces down to such a nice, simple form like that. All right, there's the solution.